Hello, Organic Chemistry 2342. We're going to continue on with chapter 19, some additional reactions we can do with alpha beta unsaturated ketones. Okay, so we can not only do that nucleophilic addition across these alpha beta unsaturated ketones, but we can do those 1,2 addition, 1,4 addition reactions. Okay, occasionally you can do it just on the carbonyl function of that alpha beta unsaturated derivative. And the way we can do that is if they're carboxylic acid derivatives and we have really good leaving groups. For example, if we have an acyl halide or an anhydride, that means that we can actually do substitution at that carbonyl instead of the addition across the double bond. So this only happens when we have really good leaving groups like chloride or acetate ion as our leaving group. So for example, in this first reaction here, we have an acyl halide that can then interact with methanol to not affect our unsaturated portion here, our alpha beta unsaturation, but actually do addition on the carbonyl to give us an ester instead. This can be done a lot of different ways, but the fact that it has a good leaving group allows it to do this. Notice if we have any other group here, like an amide, an ester, or actually a carboxylic acid where hydroxide is your leaving group, you do not get substitution at the carbonyl. You end up getting addition on the double bond, and that's going to be that 1,2 addition we saw before. So in the example of the amide or the ester here, we have the incoming nucleophile acting on it to give us our addition across the double bond, our hydrogen, of course, going on to the alpha carbon, and the hydrogen ending up on our alpha carbon and the nucleophile ending up on our beta carbon here. Okay, so using this kind of knowledge, let's continue on and do some other reactions we have. Okay, we can also use the nucleophile as an enolate ion. When our enolate ion is that nucleophile, we call it a Michael addition because we're adding that enolate across that double bond in that alpha beta unsaturated aldehyde or ketone. Okay, so in this case right here, we have our diketo compound. When we add base to our diketo compound, we end up creating our enolate ion. Our enolate ion then reacts with our beta carbon, and then once we quench our reaction, the hydrogen that was abstracted from our system here ends up on our alpha carbon, and we end up with our final Michael addition product. Okay. So again, this is an addition reaction across that alpha beta carbon, the unsaturated double bond, without affecting the carbonyl or aldehyde compound. Okay, let's look at some of the other things about this. Okay, if we look at a specific example here, we have a cyclic ketone here where we can deprotonate it with ethanol. Notice it can deprotonate on either side of here because both of those alpha hydrogens are equivalent. Once we do, we form our enol form right here. Our enol electrons can then attack the beta carbon of the unsaturation portion here. When it does that, it generates our enol form of our material here. And so we've actually made our new carbon-carbon bond. So our addition product is complete. But then what can happen is our double bond can then abstract a hydrogen from either the solvent or from the proton that was abstracted here gets transferred back to this position here, our alpha position, and we ended up adding our ketone product across that double bond, giving us our Michael addition product. So it's a alpha beta addition across that conjugated system. Okay, so let's look at a couple different other ways we can do this right here. We can do this with our diketone species, and because of the two carbonyl compounds, we can actually use fairly weak bases like hydroxide to do that, and it'll give us specifically one product because it's going to form our enolate here. That enolate is then going to attack our beta carbon here, and our hydrogen is going to end up on our alpha carbon here at the end of the reaction here. So we always get that 1,2 addition across that double bond where the larger group is on the one furthest away from the carbonyl, and the hydrogen is transferred to that alpha position, or the one closest to the carbonyl. Now, if we look at this ketone species here instead of this aldehyde here, we're going to see the exact same thing. We're going to form our enolate ion at this position here. Therefore, it's going to add to this carbon here. So we're going to have a methyl group hanging off that, and our hydrogen is going to end up on this other carbon here. So we end up with our terminal methyl group, our Michael addition carbon-carbon bond formed on that beta carbon, and our final hydrogen is added back to this alpha carbon here. Okay, so that works with diketone species, and this works with the diester. But what's also interesting is that the fact that we have a nitrile is analogous to a carbonyl compound in this function, being that it does do the electron withdrawing ability just like the carbonyl does. So we can actually use a conjugated alkene nitrile and do the exact same Michael addition. In fact, this is used very commonly in a wide variety of reactions. Here again, we have our diketo species, which when we add our base to it, we deprotonate here, forming our enolate. Our enolate then can come here and attack specifically at that beta carbon and then transfer the hydrogen to that alpha carbon at the end, giving us this chain extended diester species right here. Okay, so they all go with the same mechanism, and you can mix them together and just add your base, because the deprotonation happens between the diketone. If you're using a much, much stronger base, then you could deprotonate in other places like here or just there. Remember that the acidity of this vinylic hydrogen is really high. We're not going to deprotonate there. Now, in this case, we could deprotonate here if we used a really, really strong base, but this proton is much more acidic, and it preferentially deprotonates between the two ketones, and therefore gives us our stable enolate and our major product. Okay, so let's go through a couple different examples on how we can do this. So we can do it with our diketo species, and we always again get that addition, our carbon-carbon bond is formed on our beta carbon, and our hydrogen is always transferred to our alpha carbon here. And we can do that with amides, esters, and in this case, it's an ester, and we have a triple bond instead of a double bond, okay? So in both cases here, we have this being the most acidic proton because we're between the diketo species. Here we have a ketone, and analogous to a ketone, we have a nitrile, making this the most acidic proton, and therefore we remove the proton here and add to our carbon bond to our beta here, and our hydrogen bond is going to be to that alpha carbon here, giving us our final product right here. And when we do that with a triple bond, only one of those pi bonds is removed during the addition of the material across it, meaning we'll have a double bond left in our product here. So again, we have our diketo species, so we deprotonate at this position here. It's going to add at this terminal carbon here to give us our carbon bond, and then our hydrogen is going to add here. But because we're only using one of those pi bonds, we actually end up with the double bond in our final product. But again, our enolate is going to attack at that beta carbon, and our hydrogen is going to be added at that alpha carbon. Okay, so before we showed you can make enamines, and that's one way to make an enolate or a stable enol derivative here. We can actually use that to actually give us a nice specificity in our reaction as well. Once we form the imine here, we can use that in a 1,2 addition. This specifically is called the Stork enamine reaction. Basically, Stork said, okay, I can trap that enol in this form using the Manic base, and therefore we can get it to do that same kind of reaction. When we deprotonate, it'll add across that, giving us our intermediate, of course, and then when we transfer a proton to it, we generate our 1,2 addition product, regaining our aldehyde in our product here. Now, the last step of the reaction typically involves an acidic workup. When we add the acidic workup here, what happens is we clip off that nitrogen carbon double bond and regenerate the oxygen carbon double bond because it's stronger. And so we end up with our ketone species in our product here, even though we started with our nitrogen species in the beginning. Okay. We can use this again. It doesn't have to be an aldehyde or a ketone. It can be the analogous carbonyl compound. And in the bottom case here, we have nitrile as our analogous carbonyl compound. It does the exact same thing where it adds the carbon-carbon bond to the beta. Then our hydrogen ends up on our alpha carbon. And then when we work it up in acid, we rehydrate that imine reaction, and we get back our carbonyl compound. So it's not like a protected carbonyl because we're actually helping it activate to the system by trapping it in an enol form. And that lets us do this 1,2 addition, this alpha beta addition reaction in a much cleaner fashion. Okay. So when we're doing these Michael additions and we have esters, again, we always want to use the same base as the alcohol the ester is made out of. This is because it can reversibly add to it, giving us our sp3 hybridized carbon, and then it reverts back to our ester compound, and it can go back and forth like that. And so unless you want a mixed ester or you're clipping off the ester at the end, you always want to choose a base that is equivalent to the ester alcohol you're using. Okay. So now we've learned a lot about Michael additions, and we've learned about aldol condensations. But if we add the two together stepwise, we end up with what's called a Robertson annulation. Annulation means the formation of a ring. So what we can do is we do a Michael addition first, followed by an aldol condensation. And in that case here, we have to have our requirement for our Michael addition is our unsaturated ketone or aldehyde. And in this case, we have a ketone here. So we have an alpha beta unsaturated ketone. We have a regular ketone right here, okay? So because the acidity of this proton is very poor, because it's a vinyl group, now we have to look at the acidity of these hydrogens or these hydrogens here. The substituted hydrogens here are more acidic, therefore we're gonna make our first deprotonated species, our enolate, out of this species here, okay? So, because it's the more acidic than the one on either one of these here. So if we're making our enolate there first, so we're gonna deprotonate this first right here. That's gonna give us our anion here, which is gonna then go into our addition reaction here. So if you'll look here, this carbon I'm gonna label as A, is this carbon here as A. I'm going to label this carbonyl B right here, B, not there you are. Okay, so the key here is that we will be deprotonating this. This creates our first Michael addition product, which of course at the end of that, it protonates at this alpha position here. Now we can do a couple other things. If we deprotonated here or here or here, nothing's going to happen because there's nothing that is close enough or would make for example, this one right here is not going to deprotonate and come here because that's a 7-membered ring. If this deprotonates, that's going to make a 4-membered ring. If this deprotonates, it won't do anything. So none of these deprotonation sites will actually yield to a continuation of the reaction. But if we deprotonate here, we will now have an anion here that can form a 6-membered ring and do an addition to give us our alcohol intermediate here, okay? So only because the deprotonation here, even though it's not the most acidic proton, it's the only one that would give us a reaction, give us that 6-membered ring, that it's the only one that progresses forward. Once we form that alcohol here, we can then of course dehydrate it with heat to give our double bond. Now, it could form with a double bond here in the middle or over here, but it always forms in conjugation with the ketone because of stabilization, and therefore we get what we call a Robertson annulation. And the first step is the Michael addition followed by the aldol condensation, yielding an alpha-beta unsaturated ketone. Okay, so let's show you that in another system here. In this system here, we have something that's a little bit easier to make. Now that we have a diketo species and we have a single hydrogen here, we know it's going to deprotonate that one and only hydrogen first. Once it does that, it's going to give us our addition product. And so if we look at it here, this is our tertiary carbon right here that is giving us our addition product on that beta carbon. And then the only acidic hydrogen that will progress to give us a six-membered ring is found right here in blue. This is the only acidic hydrogen that'll give us a six-membered ring. Therefore, when it does get deprotonated, it gives us the addition product, giving us first the alcohol, and then the alcohol is going to dehydrate to give us our ketone. Notice we can't, if we dehydrate it on this side, it doesn't give us a conjugated alkene. We can't dehydrate in the middle here because we already have a tertiary, we already have a quaternary carbon here. So it must dehydrate to give us the double bond in conjugation with the ketone that we started with. Okay. So let's break this down into how to back structure these. Okay. The mechanism is actually fairly simple, where we deprotonate first to form our enolate. Our enolate does our alpha beta addition reaction here, yielding our intermediate compound here. When we deprotonate any proton, the only process that'll go forward is the generation of the six-membered derivative here, which gives us our alcohol at the end. And then when we dehydrate this, we dehydrate it such that it forms the alpha beta unsaturated conjugated system. Okay. So if we want to figure out how to make an annulation process, we need to do what we did back when we looked at Diels-Alder reaction. We have to figure out where we want the double bond in the end and where we have the double bond in the beginning, because where the double bond starts is not where it ends. It ends on the system where the ketone of our unsaturated material started. Okay, so for example, if we started with this unsaturated ketone here, this double bond will go away. And if we started with this system here as our material, where the carbon that has the carbonyl is where our double bond will appear. Okay, so for example, if we look at it here, we have this material here. It's going to deprotonate here first. This is going to come in and add to our beta carbon. Then that will form our ring and then give us this double bond is exactly where the aldehyde was. Okay, let's show you the mechanism of that. Okay, and here's another, I'm sorry, not the mechanism, but a way to draw your annulation product so you always end up with the right place and the double bond in the right place. Okay, so you want to redraw it just like you would redraw a Diels-Alder system, okay? But in this case, we want the ketone to be trans to the alkene, okay? So this alkene is going to form your first saturated carbon-carbon bond, right? And then you want to order it so that your alpha carbon, where you form your enolate, is next to this beta carbon, because that's where you're going to form that carbon-carbon bond. Then you want to order it so that your ketone or aldehyde is directed to the carbon next to the saturated carbonyl. I'm sorry, the unsaturated carbonyl, because this carbon is the one that's going to form the addition product, giving you the alcohol, and that alcohol from that carbonyl is going to leave, giving you the double bond. So when you do this, your beta carbon gives you your saturated double bond. Your initial carbonyl on whatever compound you create your enolate ends up forming your double bond here. Okay, so your double bond becomes saturated, your carbonyl becomes a double bond. So if you line them up in that way to get that six-membered ring, you'll typically get your correct products. Okay, now the last reaction we have in these condensation reactions is kind of a combination of using that Manic reaction to create an amine protected carbonyl, but we're also going to do a one carbon addition to a chain. Okay, so here we go, and it's called the Manic reaction here. Okay, so the first step to happen was we have to have a ketone, we have to have formaldehyde. It has to be formaldehyde, and we have to have some kind of primary or secondary amine. Okay, we have to have a primary secondary amine because it has to have at least 2 hydrogens to remove, so we can remove water from the system. Okay, so it can be primary or secondary. Okay, so in this case here, we're using a secondary base, and the first thing it's going to do is act as a nucleophile to attack our most reactive carbonyl, which is the one with the aldehyde, to give us this intermediate species, which is then going to dehydrate. And when it dehydrates, it gives us this iminium cation. Okay, now that activates this carbon to a reaction right here. So if we take our ketone and add a little acid, of course, goes back and forth between our eno and our keto forms. And when it forms that eno group, what happens is the electrons from the enol come in and attack that now protected carbonyl to give us our new carbon-carbon bond. And then once it does that, we kick out the hydrogen and regain our ketone. And in addition, we've added a single carbon that's from the formaldehyde, and we still have the amine attached to it here. Okay, so the combination of having that beta amino compound with that ketone gives us what we call our manic base. Okay, so the net result is we have all the carbons from our ketone we had. We added another carbon on one of those alpha carbons that came from the aldehyde here, and we still have the nitrogen cation. Notice it's not like in the imine reaction where we hydrolyze off the amine. The fact that we're not regenerating a carbonyl compound here is the fact that we're keeping that nitrogen attached to that carbon. Okay, all right, that is the end of the chapter 19 and all the different condensation reactions thereof.